4.6 billion years ago, the sun ignited from chaos, forging every atom in your body and fueling all life on Earth. But what happens when this cosmic engine dies? Its eventual extinction will erase day, transform worlds, and mark the end of our story unless you understand how a star's death creates everything we know. The countdown begins now. In a quiet corner of the Milky Way, 4.6 billion years ago, a cold cloud of hydrogen and dust began to collapse. Gravity pulled this vast drifting mass tighter, squeezing it until pressure and temperature soared. Deep inside the spinning cloud, atoms slammed together so violently that hydrogen nuclei fused into helium. In that instant, nuclear fusion ignited. The moment our sun was born, the darkness of interstellar space was broken by a new, searing light. Modern simulations like StarForge compress this ancient chaos into seconds, showing how turbulence, rotation, and magnetic fields shaped the transformation. The infant sun blazed at the heart of a swirling disk, its energy carving out a place for planets to form. Every second, the sun began converting over 4 billion kilograms of matter into pure energy, a process that continues even now. The hydrogen burning in that first flash was not ordinary. It was the start of an unbroken chain. The carbon in our cells, the oxygen we breathe, the calcium in our bones, all trace their roots to stars like this, born from the ashes of even older suns. The sun's ignition was not just a beginning for itself, but the latest link in a cosmic lineage that would one day reach Earth. From the chaos of a collapsing cloud came the light that would fuel oceans, forests, and the spark of consciousness. The story of our star begins with this fire, setting the stage for everything to come. Deep inside the sun, at its very heart, temperatures soar to 15 million degrees Celsius. Here, under crushing pressure, hydrogen atoms fuse into helium, unleashing energy that powers the entire solar system. But this energy doesn't rush straight to the surface. It begins a slow, winding journey outward. The first stop is the radiative zone, a dense shell surrounding the core. In this region, energy travels as photons, bouncing from atom to atom in a process so chaotic that a single photon can take thousands, even millions of years to escape. Each collision saps a little momentum, and the path is anything but direct. Eventually, energy reaches the convective zone, where the rules change. Here, plasma heats up and rises in vast columns, much like water boiling in a pot. As hot plasma nears the surface, it cools and sinks again, setting up rolling currents that churn the sun's outer layers. This convection shapes the visible surface and drives the bubbling, ever-shifting patterns that telescopes can capture in astonishing detail. The journey ends at the photosphere, a thin shell of plasma just 500 kilometers thick. With temperatures around 5,500 degrees Celsius, this is the layer that radiates the sunlight that reaches Earth. From the blazing core to the turbulent surface, each zone plays a vital role in sustaining the sun's balance and fueling the rhythms of life on our planet. The sun's outermost atmosphere, the corona, glows in ultraviolet and X-ray wavelengths and stretches millions of miles into space. Its temperature soars between 1 and 3 million degrees Celsius, hundreds of times hotter than the visible surface below. This defies basic physics, where heat should flow from hot to cold, not the other way around. For decades, solar physicists debated how this could be. Some pointed to magnetic reconnection, where tangled magnetic fields snap and release energy. Others argued for magnetic waves, rippling upward from the surface and dumping their energy into the rarefied corona. But from Earth, the corona's secrets remained out of reach, visible only during fleeting moments of total solar eclipse or through filtered telescopes. In 2018, a new chapter began when NASA launched the Parker Solar Probe, a spacecraft built to fly closer to the sun than any before, protected by a carbon composite heat shield withstanding over 1,300 degrees Celsius. Parker raced toward the corona, carrying a suite of instruments: Whisper, capturing wide-field images of the solar wind; Fields, measuring electric and magnetic fields; and Sweep, sampling charged particles streaming from the sun. In December 2024, Parker reached its closest pass, just 3.8 million miles from the surface, traveling at 430,000 miles per hour, faster than any object humans have built. For the first time, scientists received direct measurements from within the corona, tracing the fine structure of solar wind and observing magnetic switchbacks up close. These findings are rewriting textbooks, revealing how both magnetic reconnection and wave heating combine to supercharge the corona. Astrophotographers like Simon Tang capture the sun's dynamic outer layers in stunning detail. But Parker's in situ data is turning distant theory into concrete evidence. The mystery of the corona's heat is no longer just a puzzle. It's a frontier now within reach, thanks to a probe daring enough to touch the sun. Magnetic fields on the sun twist and snap with a power that shapes both the solar system and life on Earth. Sometimes these tangled fields suddenly realign, releasing bursts of energy known as solar flares. In the most extreme cases, the sun hurls billions of tons of charged plasma into space. Coronal mass ejections, or CMEs, these solar eruptions can travel over 1 million miles per hour, crossing the gap to Earth in as little as 18 hours. When a CME strikes our planet's magnetic shield, the results can be dramatic. On March 13, 1989, a massive CME hit Earth, driving electric currents through the ground. In Quebec, 6 million people lost power for 9 hours as transformers tripped and the grid collapsed. The blackout began at 2:44 a.m., plunging cities and towns into darkness with almost no warning. Today, scientists monitor the sun's activity around the clock, tracking flares and CMEs with satellites and ground-based observatories. The Daniel K. Inouye Solar Telescope, perched atop Haleakala in Hawaii, delivers the sharpest images of the sun's surface ever captured. Its 4-meter mirror reveals convection cells, granules the size of Texas, constantly forming and dissolving in a sea of boiling plasma. Dark sunspots, cooler than their surroundings, mark regions where magnetic tension is building. This restless surface follows an 11-year cycle, swinging from quiet to stormy and back again. During solar maximum, sunspots and eruptions multiply, increasing the risk of space weather events. Power grids, satellites, and even airline routes depend on accurate solar forecasts. The sun's magnetic chaos is not just a spectacle, it is a force that reaches across space, shaping the rhythms of modern life and reminding us that our star is far from tranquil. The sun is now halfway through its 10 billion-year life, a cosmic clock ticking toward a dramatic transformation. Over the next 5 billion years, the sun's energy output will continue to climb, about 1% brighter every 100 million years. This slow brightening has consequences. Within 1 billion years, Earth's surface will be too hot for liquid water. By 3.5 billion years from now, the sun will shine 40% brighter than today, boiling away the last of the oceans and stripping the atmosphere. As the hydrogen in the core runs out, the sun's balance will tip. It will swell outward, expanding into a red giant. Mercury and Venus will be swallowed whole. Earth's fate remains uncertain, but habitability will be lost long before the final engulfment. The countdown is set, and the inner planets stand in the path of a star growing relentlessly more powerful. When the sun's fuel finally runs out, its swollen outer layers drift away, forming a planetary nebula, a glowing shell of gas spreading into the galaxy. This is not a violent end, but a gentle release. The core that remains is compressed to the size of Earth, a white dwarf so dense that a teaspoon would outweigh a car. No supernova will erupt here. The sun lacks the mass to collapse and explode like its heavier cousins. Instead, it leaves behind carbon and oxygen, elements created in its heart, now cast into space. Massive stars end in supernovae, forging even heavier elements, iron, gold, uranium, and scattering them far and wide. All these materials enrich the galaxy, seeding future generations of stars and planets. The sun's quiet transformation is one act in a cosmic cycle where death is not destruction, but renewal. Every second, the sun converts over 4 billion kilograms of matter into energy, fueling life on Earth and powering our technology. Over 4.6 billion years, its core has burned at 15 million degrees Celsius, shaping everything from our climate to the atoms in our bodies. Scientists have mapped the sun's layered structure, documented its 11-year cycles and tracked solar eruptions that once caused the 1989 Hydro-Quebec blackout. Yet, questions remain. The corona's extreme heat still defies full explanation, and the details of solar magnetic fields are not completely understood, even with data from the Parker Solar Probe. What is certain is that in about 5 billion years, the Sun will expand into a red giant, engulfing the inner planets and ending as a white dwarf. The fate of stars like ours is written in cosmic records and scientific models, an unbroken chain from stellar birth to quiet ember. The Sun's death, when it comes, will mark not just an end, but a transformation as its material returns to the galaxy and new worlds begin.